We're now going to spend some time on one of these thermoregulatory lifestyles, namely the endothermic homeotherms. We're going to do this because the principles that we'll outline here will form the basis of a more general discussion of the biology of temperature. The fact that endothermic homeotherms regulate a constant body temperature simplifies our discussion quite a bit, so we'll start there. The problem of thermoregulation is fundamentally a problem of heat balance. If you have a body that is at some temperature T sub B, and this differs from an environmental temperature T sub E, there will be a flux of heat Q dot between the body and the environment. In the case of an endothermic homeotherm, the body temperature will be clamped and steady at some value, but the environmental temperature can be variable. If the body temperature is warmer than the environmental temperature, heat will leave the body at some rate, Q dot, that is proportional to the difference in temperature between the body and environment. We're going to set a sign convention here and just say that when heat leaves the body, that will be a negative heat flux. Obviously, if the temperature difference is reversed, that is, if body temperature is cooler than the environmental temperature, heat will flow from the environment into the body. According to the sign convention we've just set, this will be a positive heat flux. And of course, if there's no difference between the body temperature and environment, this means there will be no net heat flux into or out of the body. In this instance, the heat flux will be zero. Let's quantify this more precisely. There's a law that helps us here called Fourier's law, named after the famous French mathematician Joseph Fourier, who lived and worked at the end of the 18th century and at the beginning of the 19th century. In the biological literature, one often finds Fourier's law confused with Newton's law of cooling. Newton's law will be important to us a bit later, but suffice it to say that Newton's law describes an entirely different phenomenon than Fourier's law does. Here's the equation for Fourier's law. It states that the heat flux Q sub dot is equal to the product of the temperature difference between the body and environment, and a quantity K sub T known as the thermal conductance. The thermal conductance has units of watts per degree Celsius, and when multiplied by the temperature difference, gives the heat flux Q dot in watts. Let's graph it out on a plot of Q dot versus the temperature difference. Because both of these quantities can be either positive or negative, we have to place the graph's origin at 0, 0. This is the point where the temperature difference is equal to 0, and there will be 0 heat flux between the body and environment. And here is Fourier's law plotted out. At negative values of the temperature difference, that is where the body temperature is warmer than the environmental temperature, the heat flux will likewise be negative. As the environmental temperature warms, the temperature difference between them will decline in magnitude and the heat flux will become less negative. In conditions where the temperature difference is positive, that is, where the environment is warmer than the body, heat flux will likewise be positive, that is, it will flow into the body from the environment. This graphical representation of Fourier's law gives us a very important quantity. The slope of this curve is the thermal conductance. Applying Fourier's law to the energetics of regulation of temperature for an endothermic homeotherm is made easy because one of the temperatures, the body temperature, is held in place by the animal itself. Here's our representation of a spherical body again. Let's just assume for the moment that the body is warmer than the environment and therefore heat is leaving the body to the cooler environment. This is a physical process, and it's true whether the object is a warm, living body or a hot rock. For the body temperature to remain constant, however, this physical loss of heat has to be offset by the generation of metabolic heat. Let's call it Q dot sub M, which is a net heat input to the body. We can write an energy balance equation for this. For an endothermic homeotherm, the sum of the metabolic heat inputs and the physical heat losses must always equal 0. It's a simple matter to rearrange this equation to isolate the metabolic heat production on one side, and here we see an important thing, namely that the metabolic heat production must always equal the negative of the physical heat losses. Let's graph this out in the same way we did Fourier's law. Here's Fourier's law again, with the blue trace being these physical losses of heat. Because conservation of energy demands that metabolic heat production be equal to the negative of the physical heat losses, we can draw another graph for metabolic heat production which looks like this. It's simply the inverse of the physical heat losses. This is something quite remarkable, really, because we've taken a simple physical principle, namely Fourier's law, and allowed it to tell us something fundamental about the biology of temperature regulation. It also offers us a very useful tool. It's quite easy to measure the metabolic heat production of an animal. We've outlined earlier several ways that could be done. So, if we can measure the metabolic heat production of an endothermic homeotherm over a range of environmental temperatures, we can be assured that its slope will be the negative of the thermal conductance. So we can not only measure the metabolic heat production and how it changes with temperature, we can use this to derive an important physical quantity that limits heat loss, namely the thermal conductance. Fourier's law therefore gives us a window into the physics and biology of regulation of temperature by an endothermic homeotherm. We're not quite at a general theory for this yet, but this lays an important foundation stone for that general theory.